Thank you so much. My best efforts at Zoom have been foiled this morning. I'm going to share with you today a couple of recent projects and a little bit of backstory around what I call material ecologies and why I think that these are the kind of key to addressing a major challenge facing architecture in the near future. I'm motivated in large part by the 40 to 50% of global greenhouse gas emissions that come from our built fabric. And I think we've devoted a tremendous amount of research in the last 40 to 50 years on reducing what we call the operating carbon of buildings. That is to say that the energy used to heat, light, and cool buildings, but comparatively little to what we term the embodied carbon of buildings. And so this is the energy and carbon emissions associated with producing materials that we use to create buildings. And although in the long run, operating energy tends to be a pretty large share of the overall emissions, actually, we can think about the energy and embodied carbon going into building materials as a kind of almost a initial capital cost of building, so that unlike the operating carbon that accrues over many years of building operation, embodied carbon, the carbon we emit in actually producing building materials from raw materials, assembling buildings, is all up front. And so as we sit at the brink of a kind of climate crisis, whose evidence is all around us. We only have to look out the window these days to see it. The embodied carbon is a really serious going concern, and it's one that we really, it's only in about the last decade that we've begun to even acknowledge it. And so by way of example, the city of Vancouver just recently has begun to track embodied carbon ahead of hopefully regulating it, whereas the kind of operating energy has been regulated for many years now. And so this has been really motivating for me in my research as an architect. So it led me to co-found a company a little more than a decade ago, making sustainable alternatives to conventional masonry materials. So these are aluminosilicate clay, alkali activated clays that can be used to replace cement, which is responsible for anywhere between 5 to 7% of global carbon dioxide. And it requires kind of giving up on one paradigm, the conventional construction materials kind of paradigm on the top, in which we go mine raw materials, truck them to a production or manufacturing facility, convert them into the kind of raw materials for buildings, and then truck those to the building site, and think in terms of using materials directly from the building site for on-site production. So this would be the image on the bottom, in which we kind of use materials on site to produce materials for buildings. And so with the support of the National Science Foundation and US Department of Agriculture, because a lot of it's soil-based, we've developed some modular equipment to produce these kind of masonry materials. So these are soil-based masonry blocks that offer virtually same performance as conventional concrete masonry units. And you can see we built a few pilot homes. This is a startup based in the Bay Area of San Francisco. We've also developed precast panels, a whole range of soil-based building products that offer kind of very similar or even same performance, structural performance as conventional cement-based materials and products, but offer about close to half of reduction of half the embodied carbon of conventional concrete products. So that was a lot of my activity before joining the faculty at UBC, and persists now. But in the last 5 years or so, I've gotten really interested in another area of materials. So if the concrete block is a kind of ubiquitous material for construction used around the world with a tremendous part of the environmental impacts of building, we also use a lot of what are called polystyrene foams. So you'd be familiar with these in styrofoam cups and things like that. But sometimes people are less cognizant of the amount of these products we're using as building insulation. And so they start off like this. We used, in the US, uses around 100, it's actually up to 150 million kilograms of polystyrene annually. And that's only about 5% of the overall use for buildings, and it quickly ends up like this. So this is a waste polystyrene manufacturing facility in Abbotsford. So you may have heard some reporting on mycelium biocomposites. So about a decade ago, a couple of graduate students at Rensselaer Polytechnic Institute came up with a process to produce a kind of sustainable alternative to polystyrene foams using sawdust and mushrooms. I say sawdust, but really it's any kind of waste cellulosic material together with the mushrooms to produce these biocomposites that have similar strength, weight, and thermal resistance to polystyrene foam, but are totally naturally produced with no harmful byproducts and fully biodegradable at the end of life. So this is an image of what that kind of matrix looks like. It's actually the polysaccharides are the mycelium is just a root structure of mushrooms, and they surround in a kind of cross-linked matrix. The polysaccharides surround, in this case, sawdust particles growing in the kind of interstitial spaces. And this produces actually a very durable overall kind of structural performance. And so it's been used widely in packaging, but there's growing interest in use as actually a substitute for polystyrene-based building materials, or the insulation portion of those materials. So the process looks something like this. You can take a waste cellulose product, you need to sterilize it, or in some cases pasteurize, to eliminate competing microorganisms, and then add spores to it, and then incubate that medium, the growth medium, under controlled conditions for a couple of weeks, after which you can mold it into blocks that can be demolded after anywhere between 5 and 10 days, and then assembled into a whole that will actually grow together. And so we've been undertaking this at UBC. This is actually a greenhouse at, in the South Campus, and that's actually a landscape architecture student, Peng Fei Du, who I think had no idea that she was going to be dealing with mushrooms in this way when she got to UBC. But so we grew these kind of modular blocks, really bricks, and we took them to the Advanced Center for Advanced Wood Processing and tested out. And they actually developed about 10 or 15% higher compressive strength than comparable polystyrene foams. Of course, we're less after the compressive strength here than the thermal resistance, and they display virtually same characteristics as polystyrene foams. They're hydrophobic, so they actually repel water, which is part of the mushroom's natural defense mechanism to keep from drying out during a dry spell. But what's really interesting is that they actually will two discrete elements will actually grow together. And so this was a bag we left over a weekend in the lab, and when we came back, we were quite surprised to see that it had kind of fused together. So for an architect, this is really quite exciting because it suggests a whole range of possibilities going from a kind of modular building product into a monolithic whole. And so being architects, we got pretty curious to develop a kind of mock-up wall section, which we did for the Museum of Vancouver back, it was a bit more than 5 years ago now. So this was the mock-up wall grown of these discrete blocks, and it actually started producing the mushroom fruit. So this was a bit of a happy accident because the climate, actually the weather changed and we didn't have great climate control where we were growing it. So it got cold, and when the mushrooms get cold, they feel the onset of fall, and so they tend to fruit like many other non-fungal varieties of plants. So we rolled with it and hired a caterer and actually served portions of the wall to museum goers who actually quite appreciated. There were oyster mushrooms, Pleurotus ostriatus, which we adapted here because it's a strain that grows very well in the Pacific Northwest. And I think they weren't entirely sure that they were eating the wall as they were eating these, or actually fruits growing from the wall. It looks an awful lot like old polystyrene foam when it grows. So we also produced some benches just to kind of put them out in public. And you may have seen these in front of the UBC bookstore some years ago. So you can see here, and these were grown in kind of hexagonal shapes that would then fuse together. We had limited success getting them to fuse, and contamination is a real challenge here. So the scale at which we try to grow these things sometimes makes laboratory facilities difficult. But you can see these are some of my graduate students who in architecture tend to be quite stylish, who helped to install the installation. But what's really interesting here to me is that these products at the end of life are fully biodegradable. and so where the average age of commercial buildings in North America is currently about 35 years, it's rare for commercial buildings to last more than 70 years, which is really kind of shocking given that most architects are kind of building for the ages. We're often kind of guilty of not really acknowledging how buildings are truly used. Often due to land speculation, real estate prices and the like, buildings are demolished long before their useful lives are over. And so actually working with what in nature is a saprotroph, converting the kind of nutrients on the forest floor to become bioavailable to other organisms is really valuable in buildings as well, provided we can control it so that we don't start digesting buildings before we're finished with them. But I'm working with some microbiologists at UBC who figures large in the next project I'll talk about, to look at some of the genetic pathways we can use to perhaps turn these organisms on and off so that they can add to local ecosystems at the end of life. So we've had a lot of research assistance on this one, as well as funding from a variety of sources. And so those are a couple of projects looking at mycelium as a kind of structural material for buildings and furniture, sort of human scale on up. And I wanted to close with a somewhat more recent project looking at the application of mycelium biocomposites to the treatment of human waste. And so this has been a bit further afield for me, but is kind of strongly in the camp of circular economy. So it's also a collaboration with Stephen Hallam, the microbiologist I mentioned a moment ago, who's a Canada Research Chair at UBC Microbiology and Immunology. And it's supported by a solutions grant from the Peter Wall Institute for Advanced Studies. And I thought that in keeping with our time limit today, the most efficient thing to do would be to show you about a 3-minute video that we recently produced describing the project. And after I'll wrap up, and if you have questions, I'm happy to address them. So I'm going to go ahead and roll this. And I hope please speak up if something's wrong with the frame rate, but it should play. Let's see. So the students involved went and presented this project in New York City and won the Biodesign Challenge, which was at the Museum of Modern Art in New York in, I guess it was 2019. And this is involved about three or four faculties at UBC Vancouver: applied science, and microbiology. So that's about all we have time for today. I think that's just right around 15 minutes. It's just a slide with all the help we got for various students from across UBC. And I'll leave it there. And I'm happy to take questions now or after the other presenter today, whatever works for you, Changyan.